if you read the book and all these details, it's excruciatingly detailed descriptions of so many processes that are important. You might get a sense that ITCZ, we know everything, it's a solved problem, but I get a sense that we are just explaining what is happening and not why it is necessarily why it's happening. So we look for balances like cross-equatorial pressure gradient, absolute vorticity, and then we keep on explaining things, but it's not a prognostic. You cannot use that to say how ITCZ will move, how it will respond to global warming, for example, or even why, how El Nino and ITCZ are interacting, etc. Nonetheless, so basically I'm using that logic to argue that I'm not including all the details, but I'm presenting all the basic ideas from each section of the chapter. So near equatorial inertial instability is important because we are worried about near equatorial distribution of convection and precipitation, which are related to the inertial instability that we are looking at. So again, looking at our simple equation we derived in this background state of meridional shear, dv dt is d squared delta y dt squared, which we wrote as minus f times f minus du bar dg delta y, and we defined the ma, which allowed us to write it this way, which makes it solution that an equation for which we can look for solutions. So now let's put that in the context of the cross-equatorial pressure gradient and the potential for inertial instability. So we have gone away from the idealized explanations and trying to put the actual processes that are happening. So we're looking at a latitude and time section with the equator sitting here. So there is the high pressure and there is the low pressure, so you have a cross-equatorial pressure gradient. This is the schematic diagram that is showing forces acting on a parcel of air under the influence of a constant cross-equatorial pressure gradient. Okay, the pressure gradient remains constant, as you can see with the arrow here. P is the same length throughout this time period, right? Flow in the region that is inertially unstable, where eta over f is less than 0. So that's this yellow region. Axes representing time and latitude are drawn with orientation appropriate for northern hemisphere boreal summer. P, C, and R are pressure gradient force, Coriolis, and residual force between P and C respectively. The region where the local absolute vorticity is negative is colored yellow. The divergence convergence distributions are shown here. So it will turn out that this is very important. So start here. The cross-equatorial pressure gradient is pushing an air parcel across. So if you are moving in the direction of pressure gradient, you are near the equator, so Coriolis is small. So there is a residual force that's in the northward direction, which is going to continue to move the parcel north. But as you move north, Coriolis increases, pressure gradient is the same, residual decreases, and eventually you reach this absolute vorticity zero line, zero absolute vorticity line at time t2, where now you have balanced P and C, but inertia is going to keep it taking further, where now you have a restoring force, so Coriolis is going to get bigger and is going to pull it back. So residual force is now negative. So you see how you move it north and then you cross the absolute vorticity line and you end up with instability in the sense that there is a restoring force. But in the meantime, if you consider these changes, you know that the winds are accelerating this way, so there is a divergence, and then because of this residual force pulling it back, there is going to be slowing down, so there is a convergence. So this divergence convergence doublet, as the book calls it, are going to be important when we look at how the near equatorial convection gets set up and how the vertical meridional circulation gets set up in the latitude vertical plane. Okay, that's where the instability and convection and the 3D circulation are going to come together. So we're doing it in steps. Look simple, but they are all important. So within the scope of the theory presented above, it's proposed that three conditions are necessary to determine the location of near-equatorial convection related to the existence of a cross-equatorial pressure gradient. So we have not said where this gradient comes from. We have said it's related to the low-frequency SST distribution. But given the pressure gradient, advection of eta, absolute vorticity, across the equator by the divergent meridional winds associated with the cross CEPG, producing regions where eta or F is less than 0. This is important. The system is inertially unstable in this case. Convection itself is produced by secondary circulations in the height latitude plane that renders the system stable. So you are advecting vorticity, creating inertial instabilities, and that's going to drive convection, but convection is a way of reducing the instability. This is what happens, right? Instability is going to put its energy into kinetic energy, induced circulation, and so on to get rid of the instability, right? The SST should be close to the maximum tropical SST, but it need not be the maximum overall SST, nor even a local maximum. The atmosphere must be locally conditionally unstable in the region where the cross-equatorial advection of eta occurs. So if you advect eta, like in the Indian Ocean with a very strong cross-equatorial pressure gradient, but the atmosphere is very stably capped, then you're not going to convect. Conditional instability is necessary so that atmospheric stability does not impede the development of the rising branch of the secondary circulation. We'll see that in a minute. In conjunction with the secondary circulations, conditional instability promotes deep penetrative convection. You remember the conditional instability where we had conditional instability of the first kind and the second kind, where the negative gradients of equivalent potential temperature, we are interested in convection moisture, so we need equivalent potential temperature, indicates instability, which is going to be convecting if there is in this eta over F less than 0 created by cross-equatorial advection, and that is going to create a vertical circulation which is going to have a secondary circulation which subside, which is where the dry air from above is subsided. There is subsidence, so there is compressional heating balancing radiative cooling, because the dry air coming down is going to compress and warm, but it's in a dry environment, so it's going to lose OLR to space and be radiatively cooling. So that's the idea. So we have to put all that in the context of these things we have seen. So absolute vorticity is not on the equator, which means you have eta over F less than 0, and we have convection happening to the north of it. So you have stabilizing secondary circulation happening behind the ascent on the equatorward side. Okay, so few things to remember. Convection is on the poleward side of the absolute zero vorticity line, but not always. There are exceptions. Obviously there is the confusion here on the equator, and so on. So this figure, let me just go through it as well, shows the mean 925 HPA divergent wind fields for solstitial seasons, so June, July, August, and December, January, February. There are these properties. The near-equatorial divergent wind in the regions of CEPG is directed so that it advects countersigned absolute vorticity across the equator, so you're creating instability, and is responsible for the regions of near-equatorial anticyclonic eta, negative eta. In the northern hemisphere, you curl your fingers clockwise, you're going to get downward, so negative. And cyclonic eta in the southern hemisphere, as evident in 13.3, we will see. This advection produces regions where eta over F is less than 0, inertial instability. The divergent wind speed maximum is bisected by the eta equals 0 contour, producing a divergence-convergence doublet that we just talked about when 0 contour lies away from the equator. This pattern is consistent with the doublet found in the previous figure that we saw. So here is 13.7, and you can see Wind divergence, zero vorticity line intersecting. This is for DJF, Pacific 925 hectopascal. We will look at these sections later on. And June, July, August, sun moves north, ITCZ moves north, and so on. So this is the Atlantic and Indian Ocean sectors. There are features here where I should say that the vectors correspond to the divergent winds for the Pacific and Atlantic and Indian Oceans. Bold lines denote the zero absolute vorticity contour, zeta plus f equals 0. Magnitudes relative to the color scales on the right here, those are the divergences. So you can see that just because you pushed eta across the equator and moved it way north doesn't mean necessarily you have convection, as we'll see, because this place turns out to be very stable, and that's going to bring us to the processes that determine the distribution of absolute vorticity. We've been showing absolute vorticity line without saying how the distribution is determined. We are focused on the advection across and creation of inertial instabilities. Then we'll come back to processes that determine the distribution, and then again processes that result from the inertial instability.